Okay, Chapter 2, Section 3, Continuity. All right, so informally, a function is continuous over an interval if the graph can be drawn without removing a pen from a paper. So continuity is a concept that's really easy to describe. It's a graph that can be drawn. So if you just have a Cartesian coordinate system and you want to draw your graph, if you can draw your graph without ever lifting your pen, so say something like this, then you have continuity, right? So it's a continuous graph. So it's an easy concept to describe. It's easy to spot it, but we're going to put a bit more definition to it, or a stronger definition to it. So here's another straightforward example. So we have this function f of x. As you can see, we can just draw it without ever picking up our pencil. In particular, we would say that at x equals to 2, this function is continuous, right? And you can see that the limit as x approaches to 2 from either side is going to be equal to 4, and also that the function itself is equal to 4 when we evaluate it at x equals to 2. Right, so when the input is x equals to 2, the output is equal to 4, and also the limit as x approaches to 2 from either side, right, the unrestricted limit of this function equals to 4. So we'd say that this function is continuous at 2. Right? In fact, this function is going to be continuous for all real numbers. So when a graph is broken or disconnected at a point x equals to c, then the function is said to be discontinuous at x equals to c. So notice that in this example now, there's like a little hole there, right? So in this case, the limit does exist. This is a case where the limit as x approaches to 2 is equal to 4. However, the function is not defined at 2. Right? If we evaluate this point here, the value of x equals to 2, its output is undefined because there's a little hole there. So this is not continuous at 2. This is a case where g of x is... So you can either say that g of x is discontinuous at x equals to 2, or you can say g of x is continuous at all points except x equals to 2. Right? They're both the same thing. Here's another example. Here we have a case where the function is defined for all values that are negative, defined for all values that are positive, but it is not defined at x equals to 0. And notice that the limit does not exist as x approaches to 0 because the left-sided limit does exist, the right-side limit does exist, but they don't match each other. Right? So remember from the previous section, we can conclude that the limit as x approaches to 0 from the right-hand side of the function g of x equals to positive 1. Right? As we approach 0 from the from the right-hand side, the values approach 1. So that's the right side limit. The left side limit, the limit as x approaches to 0 from the left-hand side, as we approach 0 from the left-hand side, the limit approaches negative 1. But because they don't match, so the left side limit exists, the left side limit exists, the right side limit exists, but they don't match. So together we wouldn't be able to combine them into the unrestricted limit. The limit as x approaches to 0 with no restriction of h of x does not exist, right? Because they don't match. Okay, also note that h of 0 is undefined as well, right? There's little open holes in either direction. Okay, either way, all of this leads us to conclude that the function h of x is not continuous at x equals to 0. Also, we can conclude that h of x is continuous for all other values. Right, so x equals to 0 is the only place where we have a problem. Everywhere else, it is continuous. Right, if we just think about, well, what about 1? As x approaches to 1 from either side, it looks like the function output is always going to be 1. So it's continuous at x equals to 1. It's continuous at all other numbers except 0. Okay, so a more formal definition of what continuity is. So a function f is continuous at a point x equals to c if the limit as x approaches to c of f of x exists, 1. 2, if f of c exists, 3, that the limit as x approaches to c of f of x equals to f of c. They have to be equal to each other. All 3 are required in order for us to be able to say that the function is continuous at the point c. So a function is continuous on an open interval from a to b if it is continuous on each point in that interval, right? So we do it on a point-by-point basis, but then we kind of combine them all together and think of an interval where every single one of those values chosen inside that interval satisfies all 3 of these conditions. If 1 or 2 or 3 of these conditions fail, then we would say that the function is discontinuous at x equals to c. Okay? So when you're given a function and you're asked to determine if that function is continuous at a particular point, this is what you have to do. Step 1, 2, and 3. Figure out if the limit exists. Remember, that means that it's an unrestricted limit, right? There's no left side or right side here. It's an unrestricted limit. So you might have to determine whether the limit exists on the left-hand side, limit exists on the right-hand side, make sure they match. Then you can establish that the limit does exist as x approaches to c. Then, separate from that, you might have to figure out the value of the function at x equals to c. And finally, we have to confirm that the limit exists and it's equal to the value of the function at c. For really easy equations and functions, usually we just kind of jump over to step number 3 and that kind of does it all in once. Because on the left-hand side, you're confirming that the limit exists. And on the right-hand side, you're evaluating it and you're making sure that they equal each other. So really, step 3 has everything all in one when it's a straightforward function. Only in cases where it's a really ugly, complicated thing would you really do it, one step, then the other step, and the third step. Or if you're trying to present it in a really methodical sort of way. All right, so use the definition of continuity to assess the continuity of the function f of x at x equals to -4. Okay, so let's look at this. So this is -1, -2, -3. So this is -4 right here. And so it traces up to there and traces up to there. Let's write down some things we can tell about our function f of x at -4. So at -4, notice that f of -4, if we just evaluate -4, it'll trace from there to there and trace across to here. So that's 1, 2, 3. It traces over to 3. So f of -3 equals to 3. Okay, what about the limit? The limit as x approaches from the left-hand side, as I choose x values that start here, say at -5, the output is that one. And then a little closer to -4 from the left-hand side, the output is that one, and then that one, and then that one, and that one. So as x values are chosen from the left side of -4, and they get closer and closer and closer and closer and closer and closer to -4, but always from the left-hand side, it looks like the output values are slowly but surely climbing toward this value, and that value is +2, it looks like. Okay, so we can conclude that the limit as x approaches to -4 from the left-hand side of f of x is equal to +2. What about the other direction? So if we choose a value of x, say like over here, here's x, and I go this way and I get a little closer and a little closer and a little closer, the output values are going to steadily but consistently walk toward this value. So as x approaches to -4, but always from the right-hand side, then I can conclude that the limit as x approaches to -4, but definitely from the right-hand side of f of x, is going to be equal to 3. The left-hand limit exists, the right-hand limit exists, but they don't match. So based on this, I can just say that the limit as x approaches to -4 of f of x does not exist. Okay, so we can already stop and say we know it's not going to be continuous at x equals to -4 because we needed three things. We needed the limit to exist, we needed the value of the function to exist, and we needed them to both be equal to each other. So that third one fails, right? Well, this one fails. The limit does not exist. This one does exist. So therefore, we can conclude that the function is not continuous at x equals to -4. So we can also write the limit as x approaches -4, the unrestricted limit of f of x, compared to the value of -4, right? They don't equal each other. This side is going to be equal to 3, and this side does not exist. Okay, so we can conclude that f of x is discontinuous at x equals to 4. Okay, so f of x is discontinuous at x equals to -4. All right, let's try a different one. So the exact same graph, but now we're going to think about what happens around -2. So -2 is right around here, and we can see that it traces down here, and then it traces across this way, and so it maps over to around there. The left-hand limit, right, so the limit as x approaches to -2, but definitely from the left-hand side. That means I'm choosing values that are to the left of -2 or always less than -2. So maybe this value here, which would trace to a point there. And then I want to get a little closer and a little closer and a little closer and a little closer and a little closer, right? We want to get infinitely close to -2, but always from the left-hand side. We can see that the output values are slowly but surely marching toward 5. So the left side limit as x approaches -2 from the left-hand side of f of x is equal to +5. What about the other side? So now if I want to approach -2, but from the other side, maybe I pick this point here to begin with, that traces to there. And then I get a little closer and a little closer, a little closer, 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 infinitely closer and closer and closer and closer to -2. I see that the output values are just going to continue to get closer and closer to 5. So the right-hand limit is going to exist, and it's going to be equal to 5. The limit as x approaches -2 from the right-hand side of f of x is going to be equal to 5. So we can combine those two into the more powerful statement of saying that the unrestricted limit as x approaches -2, no conditions, of f of x is just equal to 5. So the limit exists and it's equal to 5. And now the other thing is, well, what about if we evaluate that function at -2? Well, as we can see, there's a little hole there. So this does not exist, right? It does not exist, undefined. There's a little hole there. So that means that it's not continuous there. The limit as x approaches -2 of f of x, when compared to f of -2, the left-hand side does exist and it's equal to 5, but on the right-hand side, this does not exist. So we can conclude that f of x is discontinuous at x equals to -2, right? Okay, try a different one. So use the definition to discuss the continuity of the function f of x at x equals to 1. So this time we are over here. Here is 1. Okay, so let's look at our limits. The left side limit as x approaches 1, but definitely from its left of it. So maybe I choose this x value, it traces to that output, and then maybe this one, and this one, and this one, and this one. Right? I slowly walk toward 1, but always from the left-hand side, I can see that this is consistently going to walk toward the value 4. So the limit does exist. The limit as x approaches to 1 from the left-hand side of f of x is going to be equal to 4. And then in the other side, from the other direction, the limit as x approaches to 1 from the right-hand side does exist. The output values are going to be consistently walking toward this number, which seems to be about a 1. Right? This output value there leads to a point there, and then gets closer and closer and closer and closer and closer to 1. So the limit as x approaches to 1 from the right-hand side of f of x equals to 1. Combining those two, they don't match. They both exist, but they don't match. So I cannot bring them together into one big happy unrestricted limit. The limit as x approaches to positive 1 with no restrictions of f of x equals does not exist. Right? Because it depends on what value of x you choose. Sometimes it seems to be marching toward positive 1. Sometimes it seems to be marching toward positive 4. So the unrestricted limit does not exist. Also note in this case, f of 1 does not exist either. There's a little hole there, there's a little hole there, so definitely does not work. So now if we bring them together to our statement, the limit as x approaches to 1 of f of x, and when we compare it to the actual value of the function at 1, well, they definitely don't equal each other. And in both cases, they do not exist. Does not exist. Does not exist. Therefore, they don't equal each other. They can't possibly be equal to each other if neither one of them exists. Okay, so we can conclude that this function is discontinuous at x equals to 1. Okay, now let's consider around what happens around x equals to 3. So here's 1, 2, 3. Okay, so let's look at our limits. So as we approach to 3 from the left-hand side, so let's say I choose this x value, there it is, then this one, then this one, then this one, then right, I get closer and closer and closer to 3, but always from the left-hand side. The output values are going to get closer and closer and closer to that result there, which maps to there, and that is a 3. 1, 2, 3. 1, 2, 3. So it really approaches to positive 3 from the left-hand side. And same thing from the other direction. As I choose values over here, that traces to there, and then as I get closer and closer and closer and closer and closer to 3, but definitely from the right-hand side, the output values are going to get closer and closer to positive 3. So I can write down that the limit as x approaches to 3 from the left-hand side of f of x equals to 3. The limit as x approaches to 3 from the right-hand side of f of x equals to 3. And now, because the left limit exists, the right limit exists, and they both equal each other, I can say the stronger statement that the limit as x approaches to 3, unrestricted, of f of x does in fact equal to 3. So the limit exists. However, when I evaluate my function at 3, I can see that there's a little hole there and there's a little dot there. That's indicating for me that the value of f of 3 equals to 1. So it does exist, but it's not going to match. So when I compare the limit as x approaches to 3, the unrestricted limit of f of x, and I compare it to f of 3, well, on the left-hand side, this does exist and it equals to 3. And on the right-hand side, this does exist, but it equals to 1. Therefore, they don't equal each other. So once again, I can say that this function is discontinuous at x equals to 3. F of x is discontinuous at x equals to 3. Okay, now let's consider what happens around x equals to 4. So x equals to 4 is right over here. Okay, so at x equals to 4, let's look at our limits. As x approaches to 4 from the left-hand side, right? So we choose this value, it maps to there, and then maps to there, maps to there, maps to there. Looks like it's steadily but consistently heading toward an output of 4. There. And as I choose an x value on the other side, like maybe I choose this value there, and then I slowly walk toward 4, but always from the right-hand side, then the output values, again, are consistently heading toward the same value of 4. So I can say that the limit as x approaches to 4 from the left-hand side of f of x is equal to 4. The limit as x approaches to 4 but from the right-hand side of f of x does equal to 4. Because both the left limit and the right limit exist and they equal the same number, then I can say the more powerful statement that the limit as x approaches to 4 unrestricted of f of x is in fact equal to 4. Okay. Also, the function, if I want to evaluate it at 4, I could see that f of 4 does in fact map to 4. So f of 4 equals to 4, and so now when I say the limit as x approaches to 4 of f of x, and I want to compare it to f of 4, then it matches. This is true. The left side does exist and it equals to 4. The right-hand side does exist and it equals to 4. So finally we have a case where the function is continuous at 4. Okay, so we can say the more powerful statement of identifying where all the places where this function is continuous, and it's continuous at 4, but it's also going to be continuous everywhere else except for a few places we've identified where there's a problem, right? So we can say that f of x is going to be continuous except, and we saw that there was a problem here at -4. The problem in -4 started by the fact that the limit did not exist, right? One limit is this direction, the left limit goes toward 2, the right limit goes toward 3, the limit does not exist, so this is definitely not continuous there. So let's put an except at x equals to -4, and we saw that that problem there is that the limit doesn't exist. Also, there's a problem here. It says continuous at -2, at x equals to -2, and it's discontinuous there because although the limit does exist, the function is not defined there. That's why there's a little hole there. So it does not. The function is not continuous at -2. Also, the function is not continuous at +1. And it's not continuous at +1 because the limit doesn't exist and because the function is undefined at +1. So all kinds of problems. And then finally we saw that the function is also discontinuous at x equals to +3. And this case, equals to +3. In this situation, the limit does exist and it equals to 3. And the limit does exist, the value of the function does exist, it's equal to 1, but they don't match, right? So there's different reasons for each one of these, but the result is the same. The function is discontinuous at all these places, or we can say the more powerful statement of saying that the function is continuous for all real numbers except these ones, right? You can put a little list of things. Okay, notation-wise, instead of writing this whole thing down, it would be a little easier to express this whole thing this way. F of x is continuous at, you can just do this, at such that, and then you just put conditions. So this means x such that, and then you put some conditions over here. So you can begin by saying x is a real number, and then that you say x cannot be equal to 1, x cannot be equal to 2, -2, -4, and +3. So you can just kind of bring it all together this way. Okay, it's okay if you write it all out, or if you start to see some notation that helps you reduce this, that's fine. We can also think about interval notation to express the exact same thing, right? So we could say that it is continuous for starting at -infinity and then heading out to -4, union it with, and then from -4 out to -2, and then union it from -2 out to +1, and then union it from +1 out to +3, and then union it from 3 to infinity. Right? So this is another way of expressing the same thing. F of x is continuous for all real numbers, except that x cannot be 1, cannot be -2, cannot be -3, cannot be -4, and it cannot be +3. Or you can use this notation. This is indicating that it's all real numbers. Here, let me put it on the underline. This right here is indicating it's continuous for all values to the left of -4, from -infinity to -4. And then this part is saying that all values between -4 and -2, that would be all of these values right in here, right? And it's parentheses and union, so it's leaving out a little hole there. It's not continuous at -4, and it's not going to be continuous at -2. So from -2 to +1, that would be these guys. All the values in that little interval in there are continuous. And then next we're saying, well, from +1 to 3, from +1 to 3, then it's continuous in between there for any value in there. And then finally the last segment says from 3 all the way out to +infinity, it's also continuous there. From 3 to infinity, so from there to there, also continuous. Okay, so different ways of expressing the same thing, but hopefully that makes sense. All right, moving on. Use the definition of continuity to discuss the continuity of a function at the indicated point. Okay, so f of x equals to x plus 3. That is clearly a linear equation. Right, so f of x equals to x plus 3 is something that fits the form of y equals to mx plus b, right? This is a linear equation where m is the slope and 0 comma b equals the y-intercept. So for us, we have that m equals to 1, right? There's this invisible 1 there if there's nothing else. So m equals to 1, and we have that 0 comma 3 is the y-intercept. So if we have that, then we can easily just get a rough sketch. So we know it goes through the point 0 comma 3. It's a linear equation. It's got positive slope, and I can do like a little triangle here. Say rise over run is 1 over 1. Maybe the line looks a little weird. 1 over 1. So this is going to be equal to the point 1 comma 4. Here we go 1 unit this way, 1 unit up. So 1 unit and 1 unit. So we get to 1 comma 1. Okay, so this is just a rough sketch of what that graph looks like. But when we consider the limit as x approaches to 4, so here is, say this is 4 right here. The limit as x approaches to 4 from the left-hand side, you see that it's going to be these values there. And the limit as x approaches to 4 from the right-hand side, it's going to approach those values there. Either way, we see that it's going to approach this point there. And what's that point going to be? Well, it's a linear equation with this as a slope. So note that f of 4 is equal to 4 plus 3, which is equal to 7. And because this is a linear equation, also it's a type of polynomial, we know that the limit does exist and the limit will be equal to the value of the function. Right? So the limit as x approaches to 4 of x plus 3 is going to be equal to 7. And also we know that f of 4 is 7. Therefore, when we bring it together, we could say that the limit as x approaches to 4 on the function x plus 3 will be equal to f of 4. Right? That's true. They both equal 7. So we can say that the function is continuous at x equals to 4. Is continuous at x equals to 4. So we got to bring a variety of ideas here. One, it's important to recognize that the equation is the equation of a linear equation. Also, it's important to note that it's a type of polynomial, x plus 3, and we already learned in a previous section that whenever we have a polynomial, the limit is going to exist, and it's going to be equal to the value of the function evaluated at that point. So we bring those things together and we can conclude that this function is definitely continuous at x equals to 4. Being able to graph it is also a nice way to figure out whether a value is continuous at a point or not. All right, moving on. Use the definition of continuity to discuss the continuity of the function at the indicated point. So at x equals to negative 3. Note that g of x equals to x squared minus 9 all over x plus 3 is the same thing as x plus 3 times x minus 3 all over x plus 3. Okay, now if we think about the limit as x approaches to negative 3 on x plus 3, let's back up. The limit as x approaches to negative 3 on x squared minus 9 all over x plus 3 is equal to the limit as x approaches to negative 3, and then we can factor this. X plus 3. Okay, and now the question becomes, can we cancel these? Can we cross them out? And the answer is we can, because the fact that this limit is here is we're pointing out that we're not going to attempt to evaluate this function when x equals to negative 3. Over here, when there was no limit, there was a question mark, right? Here, what if x is equal to negative 3? Then you'd end up with a 0 in the denominator, and that is questionable. We want more information there. But when we're working with a limit, we are already saying we're not going to let x equal to negative 3. We're not interested in that. We just want values that are close to negative 3. Like maybe x equals to negative 2.9999, for example. That's close to negative 3, but not equal to negative 3. In which case, we would get a very small positive or negative number down here, depending on the value of x, but it would definitely not be 0. Therefore, in those cases, you are able to cancel these out. So you'll be able to get this to be equal to x approaches to negative 3 of x minus 3. And so now this is a polynomial, and we know from previous section that when we have a polynomial, the limit will exist, and it's equal to just plugging it in. So now the limit will be equal to blank minus 3. So let's put it in red. So now we just plug in this minus 3. Right? So this is the minus 3 from in there. I'm just plugging it into the x, which gives me a limit of negative 6. So the limit does exist. It equals to negative 6. However, when we evaluate the function at negative 3, we're going to get a 0 in the denominator. g of blank equal to blank squared minus 9 all over blank plus 3, and then we try and evaluate this at x equals to negative 3, we're going to end up with a 0 over a 0. So that's an indeterminate form, undefined, for this value. So the function is not continuous at x equals to negative 3. The limit exists, but the value of the function is undefined at negative 3. So g of x is discontinuous at x equals to negative 3. So g of x is discontinuous. So true, you could have just stopped here if this was, if they just asked you to figure out whether it's continuous or discontinuous at this point, and you noticed that the function isn't even defined at negative 3, you could have just stopped here and said, okay, it's discontinuous. I just added this extra little bit for fun, just to point out that the limit does exist. The problem here is that the function is undefined there. Good. So this is going to be a case that if we graph this, there's just going to be like a little hole. This is some sort of a graph, and then it's got a little hole when x equals to negative 3, and that's why the function is discontinuous there. Okay, so limit exists, but the function is not defined at negative 3, so the function is discontinuous at x equals to negative 3. Okay, let's try a different one. What about this one? Use the definition of continuity to discuss the continuity of this function. Okay, so let's figure out what happens at various points. So first of all, note that when x equals to 1, we end up with a 0 over a 0, which is undefined. So I already know that it's going to be discontinuous there. Let's think about the limit, though. So let's approach this from the left side and the right-hand side. Okay, but let's consider the limit. What happens to the limit as x approaches to 1 from either direction? So let's begin from the right-hand side. Let's find or think about the limit as x approaches to 1, but from the right-hand side of this function, x minus 1 divided by x minus 1. Okay, so note that if I'm approaching x from the right side of 1, then the values of x are going to be a little bit bigger than 1, like 1.5, 1.4, 1.1, 1.01, 1.001, right? That kind of thing. Getting closer and closer and closer and closer to 1, but always just a little bit bigger than that. So if we take, one example, like x equals to 1.01, that's just one of an infinite number of choices you could make. But if you make that kind of choice and you input a value of 1.01 into there, and you take 1 away, we're definitely not going to get 0, because this is not 1. It's never going to be 1. So it's always going to be a number that's a little bit bigger than 1 minus 1, would be a very small positive number. Always positive. Therefore, the absolute values make no difference. So they're not needed. Right? In this case, because I'm always choosing values bigger than 1, the absolute values are unnecessary, so I can just get rid of them and say that in this case, when I'm approaching 1 but from the right-hand side, that I can just get rid of them and just write x minus 1 over x minus 1. Okay? All right, and then once again, because I'm not choosing 1, I'm promising that I'm never gonna let x equal to 1. I'm just getting really close to 1. Then these two things are always going to be the same number and the same sign and everything. They're always going to be a very small positive number, which means that they will cancel and reduce to just 1. So this limit just equals to 1. Right? These guys just cancel. So the right side limit does exist and it equals to 1. What about the other direction? What about the left side limit? The limit as x approaches to 1, but always from the left-hand side, of the absolute value of x minus 1 divided by x minus 1. Okay, again, the values of x are going to be very close to 1, but always to the left of it. So one tiny example. One example could be that it could be 0.99, right? It's just one example of many, right? I can choose an infinite number of values as they get closer and closer and closer and closer to 1. So if I do that, and I'm just taking one little example, that x value could be selected to be 0.999. Notice that 0.99 minus 1 is going to be a very small negative number. Definitely negative. It's going to be a tiny, teeny little decimal, but always negative because I'm always choosing values that are a little bit smaller than 1. So I can replace this absolute value by saying that it's going to be equivalent to the following. It's the limit as x approaches to 1 from the left-hand side is going to be x minus 1, but always times a negative 1. Now, why do I have to throw in that extra negative 1? I know that that can look a little confusing. Remember that we just established that this part inside the absolute values is always going to be a very small negative. Small negative number, right? A very small negative decimal. But then what does the absolute value do? It turns it into a positive. How do you turn a small negative number into a positive? You have to multiply it by a negative 1. I know that this little subtraction of the input minus 1, because of the special selections of the input, I know that this part in here is going to be a very small negative. But then if I multiply it by negative 1, it makes the whole thing a small positive number, right? That's what the absolute values is going to do. So we take that and we divide it by x minus 1. Again, because x is going to be a value that's to the left of 1, this denominator will also be a small negative. But they're identical. And x is never allowed to be actually 1, so this is never going to be 0. Therefore, I can just cancel these guys. So this will reduce with that, and the only thing that survives is this negative 1. So I can conclude that my limit is going to be equal to negative 1. So the right side limit of my function exists, it equals to 1. The left side limit of my function exists, it equals to negative 1. Therefore, the limit does not exist, and also it doesn't exist at that point. So for all those reasons, we can conclude that this function is definitely discontinuous at x equals to 1. Right? So the function is not defined at x equals to 1, and also the limit does not exist at x equals to 1. Let's graph this one. Okay, so this is the graph that we get. Here it is. H of x equals to the absolute value of x minus 1 divided by x minus 1. So here it is in blue. So 1 is sort of this division line. Everything to the right of 1 is going to be equal to positive 1. Every input value to the left of 1 is going to result in an output of negative 1. So we can see that here. Every value of x to the right of 1 always gives you the same output of 1. And the limit as x approaches to 1 from the right-hand side will approach 1, positive 1. On the other hand, for every input value to the left of 1, the output value is going to be negative 1. And so the limit as the input value approaches positive 1 from the left-hand side will be equal to negative 1. So at exactly x equals to 1, there are two little holes on both sides, so the function is not defined, and also the limit does not exist as x approaches to 1, right? The unrestricted limit. The limit from one side exists, the limit from the other side exists, but the unrestricted limit does not exist. Okay, but we can have one-sided limits, as we just saw in the previous case. We are allowed to have one-sided limits, so a function is said to have to be continuous on the right at x equals to c if the limit as x approaches to c from the right side of f of x equals to f of c. And a function is said to be continuous on the left at x equals to c if the limit as x approaches to c from the left-hand side of f of x equals to f of c. Okay, so if we just restrict to one side, then we can have a one-sided continuity. So a function is continuous on a closed interval from a to b with brackets on the ends to show that that it includes the endpoints. If it is continuous on the open interval from a to b and is continuous both on the right of a and the left of b. So here's a nice example of that. Here we have this function here in blue, and it's definitely continuous everywhere between -1 and 1, right? So any value, any x equals to c value chosen anywhere inside here, we let c equal to this point, and you're like, is the function continuous at x equals to c? Yes, it is. Anywhere within -1 and 1, continuous everywhere. But now there's also dark circles at the edges here, and so we see that for -1, the limit as x approaches -1, but from the right-hand side does exist, and it approaches to 0, and f of -1 does exist, and it equals to 0. So the one-sided limit exists, and so the function is continuous from the right side of -1. And over here, same thing. As x approaches to -1, but definitely from the left side, right? I'll write that one down. The limit as x approaches to 1 from the right-hand side of my function exists, and it's equal to 0. And also f of x, x of 1 is equal to 0. Therefore, the function is continuous on one side. It's continuous from the left-hand side. So together, this and this both can allow us to say that the function f is continuous on the closed interval between -1 and 1. Okay, so hopefully that's clear. Let's one more example. How about this one? Here we see that the function is continuous for any number in here, any value, say for example 3. If someone asked you, is this function continuous at 3? Then, from the picture we can easily tell, and then we could do some math to confirm it. But we could see that the limit from the left does exist. It goes to that point. The limit from the left and from the right both exist, and they go to that point. The value is defined at 3, so it's definitely continuous there. It's continuous for all positive real numbers that way. And then what about at 0? Okay, so the limit as x approaches to 0 from the right-hand side does exist, and it's equal to 0. And the function is defined at x equals to 0, and it equals to 0. Therefore, we can say that this does have a one-sided continuous, does meet the definition to being continuous on one side. And so we can conclude that the function is continuous on the interval between 0 and infinity where there are brackets around the 0. So we want to say that the limit as x approaches to 0 from the right-hand side of g of x is equal to 0. And also g of 0 does in fact equal to 0. So we can say that it's continuous from one side only. It's continuous from the right-hand side at 0, which allows us to make this conclusion. Okay, so hopefully that's clear. Okay, the general continuity properties. So if two functions are continuous on the same interval, then their sum, their difference, their product, and their quotient are continuous on the same interval except values of x that make the denominator equal to 0. So the sum, the subtraction, the multiplication, or the division of two functions that are continuous on the same interval will continue to be continuous on the same interval, with the only condition that we have to be careful about is the case where we're dividing them both, because we have to make sure that the denominator doesn't accidentally become 0, right? So that's the only thing we have to look out for. Other than that, we can add two functions, subtract them, and multiply them. And as long as we started out with two functions that were continuous on an interval, we will continue to get a final result that continues to be continuous on that same interval. Okay, theorem 1. continuity properties of some specific functions. So here's a bunch of properties that we get to just use. You don't have to worry about proving them or anything, so that's good. We just have to understand them and use them and apply them. So a constant function f of x equals to k, where k is any constant, is continuous for all values of x. Okay, hopefully that one is really straightforward. Anytime you have f of x equals to k, where k is a constant, if you think of its graph, it's going to be the horizontal line y equals to k. So in a case like that, then the function is going to be continuous for all real numbers. Right? A little example is if f of x equals to 7, that's a continuous function, and it's just going to be the horizontal line y equals to 7. Right? Let's graph that. Right? So here's the line y equals to 7, and clearly it's continuous everywhere. And that's going to be true regardless of what that value is. It could be a 7, it could be a 5, it could be a -3. It doesn't matter. As long as you're choosing a constant here, not a whole number, but a real number, then it's going to be a horizontal line. So let's let a be a slider. Let's let this equal to a. And then no matter what value you choose, you're going to end up with a horizontal line. And so therefore the function is going to be continuous. Okay, moving on. B, for any positive value, f of x equals to x to the nth power is going to be continuous for all x. Again, we don't have to worry about proving it, but this is a really important statement that if we're given any function that fits the form x to the power of n, where n is a positive integer, meaning 1, 2, 3, 4, 5, all of those values, that we will get a continuous function. So here's a little example, f of x equals to x to the 5th power. Because it fits this form, this is where n equals to 5, then this is a continuous function. Okay, let's graph that, x to the 5th power. X equals to x to the power of 5. So this is what x to the power of 5 looks like, and as you can see, it is continuous. There is no holes, it doesn't break off, it's continuous for all real numbers. So this is going to be true whether you choose x equals to 5 or x equals to 3 or x equals to 7 or x equals to 2. As long as they're counting numbers, then you'll always get, as long as they're positive counting numbers, you're always going to get a function that is continuous. Go from 1 to 20 by 1s. So when a equals to 1, this is going to be x to the power of 1, and so you'll get a straight line. And then as a changes, we see that we get a parabola. That's just going to be x squared, then x cubed to the 4th. And so you see that this is the pattern that happens. This is what happens as you raise things to a power. So this is x to the power of 18. It looks an awful lot like x to the power of 2. Right? So that's what we should notice when we are looking at x to the power of a, and we look at all the values where a is a 2, a 4, a 6, and 8. They look a lot like this. They have this same sort of shape. They just become a little more squared off with each one. So, for example, let's change this to 2's. 2. So now if I just go by 2's, see what happens? It just gets more and more squared off as I raise the powers to be higher and higher and higher. Good. On the other hand, if I have odds, so let's say I start off at 1, and I'm only looking at all the odd powers, so 1, 3, 5, this is what we get. Here is a equal to 3, and then 5, and then 7, and then 9, and so on and so forth. So you can see what happens. Again, they all have that same sort of shape, except they get a little bit more squared off. Okay, so that's what happens to the general pattern. That's the general pattern that we see with the graphs. But the point of this was to point out that they're always going to be continuous, no matter, regardless of their shape. Right? No weird discontinuities. So back to this guy. So part B says that if we have a function of this form, x to the power of n, where n is a positive integer, then we can be guaranteed that f of x is going to be continuous for all real numbers x. Next, we know that a polynomial function is continuous for all x. That's a very, very powerful statement. So anything that fits the form of a polynomial is going to be continuous for x. Good. A rational function is continuous for all x except the values that make the denominator 0. Okay, that's another really important statement that we can use. So here's an example. Here's a rational function. The numerator is a polynomial, the denominator is a polynomial. This statement is saying that this function is going to be continuous for all real numbers except maybe right here where the denominator equals to 0. And in this case, for instance, when x equals to 1, we're going to get a 0 in the denominator and the function will fail to be continuous there. So this function is continuous everywhere except at x equals to 1. Okay, E, for n an odd positive integer greater than 1, this is continuous wherever f of x is continuous. So the nth root of f of x is going to be continuous as long as n is an odd positive value, positive integer, n being a positive integer. Okay, so what does that look like? For instance, if we're looking at the cube root of f of x, or the 5th root of f of x, or the 7th root of f of x. So if we have an odd counting number there, positive counting number, then this is saying that the whole result will be continuous whenever the part inside, the f of x, is continuous. Good. On the other hand, the other case for part f says that if this is an even one, so if we have the square root of f of x, or the 4th root of f of x, or the 6th root of f of x, well, then we do have to be careful because this is saying that our result will be continuous whenever f of x is continuous, and we have one more restriction, one more thing we have to be careful about. We have to make sure that the part inside the radical is non-negative. It could be a 0 or something positive. It just can't be a negative, right? Remember that if we have the even root of a negative number, we're going to go into imaginary land, and we'd like to avoid that for now. So if we have, for example, some number here, let's say that this is some even root there, and this is a negative number in here, that this will result in an imaginary number. And we want to avoid that for now. So we just stay away from that and say we're not going to consider those. We're going to avoid those. Okay, so let's think about several of these examples. Determine whether the function is continuous or not. This one's easy because it's a polynomial. And one of our properties indicated that all polynomials are continuous everywhere, right? That would be this property here. Property C, a polynomial function is continuous for all values of x. So I can conclude that this one must be continuous for all values of x. What about this one? Determine whether this function is continuous or not. Okay, so it's a rational function. And one of our properties indicated that all rational functions are continuous on all real numbers except whenever the denominator equals to 0. And we can see that this is going to result in a 0 whenever x equals to 3 or whenever x equals to -1. Right? So let me point that out. So note that when x equals to 3, put a 3 there, put a 3 there, put a 3 there, put a 3 there, we end up with 3 over 0 times 4, which equals to 3 over 0. Okay. And if we tried -1, -1 there, -1 there, -1 there, -1 there, we would end up with -1 divided by -4 times 0, which equals to -1 over 0. Either way, we have a 0 in the denominator, and so one of our properties indicated that our function is going to be continuous everywhere except at the places where the denominator equals to 0. That was this property right over here, property D. The rational function is continuous for all x except those values that make the denominator 0. So by property D, we can conclude that this function will be continuous everywhere except at those values. So f of x is continuous Okay, determine whether this function is continuous or not. Okay, so we have inside here, this function inside here, f of x equals to x squared minus 9, that's a polynomial. Polynomials are continuous for all real numbers. And also this is an odd value. So therefore, the whole thing is going to be continuous for all real numbers. This is going to be an example. This is an example of this little property here. For n being odd, a positive integer greater than 1, then the nth root of f of x is continuous whenever f of x is continuous. And in our case, f of x is a polynomial, so we get to use property C, that a polynomial function is continuous for all real numbers. So for those reasons, we can conclude that f of x is continuous on all real numbers. So x squared minus 9 is a polynomial. Therefore, the cube root of x squared minus 9 is also continuous in all real numbers. Determine whether this function is continuous. Okay, so the part inside the root, is definitely a polynomial. So again, we have a case where this part inside here is a polynomial. In fact, it's a linear equation, which is a type of a polynomial. So it's continuous on all real numbers. However, note that now we have an even root. Right? There's this invisible 2 there. It's an even root. So we got to make sure that we don't plug in any negative numbers. I got to make sure that whatever goes inside there has to be positive in order for us to get an answer. So I got to guarantee that x plus 1 must be greater than or equal to 0 for all the values that will give us a result that's 0 or greater. And now if I solve for x, we get that x is greater than or equal to negative 1. If I subtract 1 from either side. So these are the input values. Anything that is greater than or equal to negative 1 will result in a positive number inside the even root, thereby giving me a value that is continuous. Okay? So f of x is continuous for all x greater than or equal to negative 1. All real numbers that are greater than or equal to negative 1. Okay, theorem 2, sign properties on an interval from a to b. If f is continuous on a to b, and f of x does not equal to 0, then either f of x is strictly greater than 0 for all x values in a to b, or f of x is strictly less than 0 for all x values from a to b. What in the world is this saying? Okay, let's come up with a little picture that kind of describes what this is. So let's say that we have just a really rough sketch here. Let's say we have some function. So let's say we have some function defined in this section. And I don't know what it will be. It could be any function here. Maybe it goes up and comes down like that. That could be my function f of x, for example. Okay, but let's stick to these descriptions. So the function is continuous. There it is. Okay, so this one is continuous from a to b. Well, so let's say that f of x is continuous from a to b, and we know that the function does not equal to 0. So here is the point. If the function is continuous, that means I can draw it without lifting my pencil, right? And it never equals to 0. So it can never be equal to, I can get close to 0 and maybe jump above 0 and then come down. So either I start off above the x-axis like I did here, and then I always stay above the x-axis because it can't be 0, right? There's no way that my function f of x could ever be a negative down here, because in order for my continuous function that is up here to ever make it down to down there, below the x-axis, I would have had to touch 0. And we're being told that the function was never equal to 0. On the other hand, let's say I start down here. If I start down below the x-axis and it's a continuous function, I'm negative. I'm always negative. Once I'm negative, I could never be positive, because in order to go over to the positive side, I would have to cross the x-axis, and we're being told that the function was never equal to 0. The only way to be able to go from positive to negative and not touch the x-axis would be to do some sort of a jump thing like that. But then we're being told that this function is continuous, so that's not allowed either. So if we have a function that's continuous on a to b, and we know that it is never equal to 0 on a to b, then the function is always positive or the function is always negative. That's what this is saying. Okay, let's see an example of how that's useful. Solve this inequality. Figure out when this is going to be strictly greater than 0, right? Figuring out when this is strictly greater than 0, that's the same thing as asking you to figure out when is this positive. When is x plus 1 divided by x minus 2 positive? Okay, so keep in mind that in order for a fraction to be positive, one of two things has to happen. We could have a positive number and then divide that by another positive number. That will be equal to a positive number. Or, and then this is the other trickier one, what if we have a negative number divided by another negative number? That's going to be equal to a positive, right? Likewise, in order for us to get a negative answer out of a fraction, I could have a negative divided by a positive. That would give me a negative number for my fraction. Or the other way around, I could have some positive number divided by a negative number, and then that would give me a negative number. Okay, so in order to figure out this thing, there's a couple of ways to do it. The book likes to push the idea of finding the partition points of this function, figuring out what values are going to result in either a 0 in the numerator or a 0 in the denominator. And that's really easy in this case. So note that note that x equals to -1 results in -1 plus 1 divided by -1 minus 2, which results in 0 all over -3, or just 0. And also all the places where the denominator is 0, or all the places where the function is undefined. And again, note that 2 plus 1 divided by 2 minus 2 equals to 3 over 0, which is undefined. Okay, so this is a rational function. It is continuous on all real numbers except x equals to -2, except equals to 2. So if we think about the horizontal axes of its graph, so I'm not going to actually graph the function, but I'm going to think about the x-axis, right? So there would be some graph above or below it that is connected to this. And then if I think about where these values are that I just identified, so there's this -1, here's -1, let's say that that's 0, and then there's 1 here, and then there's 2 there. Okay, so I know my function is definitely equal to 0 here, so I know that when I plug in a -1 into this function, I'm going to get a 0. So I know one value in my function. And I definitely know that the function is undefined at x equals to 2, so there's like a little hole there. And that's it. There's no other place where the function equals to 0. Otherwise, I'd have another dot somewhere on here. And there's no other place where there's a hole on the x-axis. These are it. So because the function f of x, this rational function, is continuous everywhere, then that means that if, for example, I went out and found one more point, let's say that I wanted to test this point over here, let's say it's -3. If I find out that -3 turns out to be positive, that would mean that my function would have to stay positive all the way through there until there, right? I cannot switch over to the other side because that would involve crossing the x-axis either through having a value that equals to 0 or through some sort of hole, right? That's the only way you can get to the other side. Or the other way around, if I found out that at -3 the function was negative, then that would mean that the function lives down here below the x-axis, except potentially there, that it goes toward -1, right? So it's all or nothing. In this zone, to the left of -1, the function will always be positive or always be negative. It cannot be both anymore. So all we have to do is think of a test point. So maybe for -3, it's just an arbitrarily chosen value at -3. Let's do a test point at x equals to -3. So I plug in -3 plus 1 divided by -3 minus 2. And really all I really care about is figuring out whether it's going to be positive or negative at this point. So I'll end up with -2 divided by -5, which equals to some positive 2/5 positive. Okay, so that means that my graph has to stay above the x-axis to the left of -1. I have discovered that this is going to be some point there. I found one point on the function, and it's also continuous. So that means that this function on this side maybe does this kind of thing. I don't know what it looks like, but I definitely know that it's got to stay above the x-axis. It could not cross down below the x-axis because, as I mentioned, we only know of one point where it touches 0 and another point where it's a little hole. There is no other place here where it's equal to 0, and there are no other little holes in this little segment, and I have that one point is positive, so the whole function must be positive there. Okay, so what this does is that the -1 and the 2 are partition points. They divide up the number line, the domain, into segments. This segment there, and in that little segment, the function is always positive or always negative. It's also going to break it up into this little segment, and in this little segment, the function will also be either always positive or always negative. Maybe my function comes down, touches the -1, and then turns around and comes back up and does some fun stuff over there until it goes back to that hole. Or maybe it punches through to the other side and does some stuff down there, always stays negative until it comes to there, right? So in this green segment, the function will always be negative or always be positive. It's up to us to figure it out. So now we just have to pick another test point. Why not pick any point in here that's definitely in this segment, something convenient and easy? So why not choose 0? That's always a nice, fun thing to test. Test point x equals to 0. And that's going to be really easy to plug in. 0 plus 1 divided by 0 minus 2. And so we end up with 1 over -2. 1 over -2, which is just equal to -1/2, which is negative. Okay, so what we just discovered is that this value at x equals to 0 definitely results in a negative 1/2. So I know that the function never equals to 0 in this green segment anymore. There is no holes, and I know that the function is continuous in that area. So that means that it must be negative throughout this whole thing. I don't know, maybe it does that. I don't know what it does, but it definitely stays negative. That's what's important here. It stays negative. Good. Okay, and then finally we have this final segment over here. This little segment over there. We need to test a value there. So pick another test point that's definitely on this side of 2, something easy, about 3. Nice easy test point. So we'll end up with 3 plus 1 divided by 3 minus 2, which turns into 4 divided by 1, which is a positive number. And that's all that matters. Now I know that at this point there's some positive value, and so I know that this will punch through this hole, go to the other side, and then it's going to be positive on that side. And I don't know what the graph will do, but it'll definitely be positive. That's all that really matters. So in fact, when you're doing these things, we don't try and guess what the graph looks like. All we really try and do is figure out the signs. So I know that the function is 0 here and undefined there. So I put a 0 with a slash. Undefined there and 0 there. And I know that the function must be positive on this side, and that the function must be negative on this side. And I know that the function must be positive on this side. So that's what we discovered. Okay? Our outputs will be positive to the left of negative 1. It will be negative between negative 1 and positive 2. And that the function will be positive for values that are greater than 2. One more way to tackle these things. When they get really complicated, I think this other method provides a way to kind of break it down into little pieces that are easier to deal with. So remember, our goal is to recreate this part right here with the reds to figure out when the function is positive, when it equals to 0, when it's undefined, negatives. Okay, so just to recreate this little part, another way to do this, to do the following. Okay, so we have f of x equals to x plus 1 over x minus 1. So what we want to do, or the way I would suggest another alternative to this, is to draw several number lines. So the first number line we're going to do is to think about this. So this first number line is going to be for just one of them. So it's going to be x plus 1. Think about when that equals to 0. So I'm going to go over here and write it there. And so it's going to be at negative 1. So I'm going to put 0 at negative 1 because that's when this becomes 0. And then I think about numbers that are bigger than that value. So if I plug in numbers like 0 or 1 or 2 or 3 or 4, I put a 4 there, a 5 there, all I'm thinking about is whether it's going to be positive or negative. So for all numbers to the right of that one, we're always going to get positive numbers. So positive, 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 positive. And then values to the left of that are always going to be negative, 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 negative. Right? If we're putting a negative 4 plus 1, that's going to be negative. Okay, next, right below it, draw another number line. And then trace down some of the key values like that 0, the 1, and the 2, and the 3, and the negative 1, and the negative 2. Okay, this number line is going to be for the other polynomial here. That's this one. So this one's just going to take the x minus 2 into consideration. Think about when that's a 0. So that's a 0 whenever x is equal to positive 2. Right? That's when that's going to be a 0, so put a 0 there. And now I think about numbers that are to the right of that 0, like a 3 or a 4 or a 5. those are going to be positive values over there. Positive, 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 positive. And then values to the left of that are always going to be negative, right? Think about a 0 or a -1 or a -2. These values are always negative to the left of that. Okay, finally, think about one more number line. And again, trace things down. So there's where the 0 goes, that's where the 1 goes, that's where the 2 goes, that's where the 3 goes, -1, and then -2. Okay, and now this final one is going to be for what we're interested in, the ratio of the two. So x plus 1 divided by x minus 2. Now the beauty here is that we're not really interested in the actual results of dividing these two things. We're just interested in figuring out whether we get an undefined, a 0, or a positive or a negative number. So let's look at our zeros. We end up with a 0 there over a negative number, so the division of the two is going to result in a 0 here. Okay, over here at x equals to 2, the denominator is a 0, the numerator is some positive number, so we get a positive divided by 0. This is going to be an undefined there. Good. Okay, and then we end up with these three regions. When we pick x values that are to the right of the 2, we're going to end up with some positive number in the numerator divided by some positive number in the denominator. So I know that these are all going to be positives to the right of this value. In the middle here, if I choose a value like 0 or 0.5 or 1, any number in here, I know that the numerator is going to end up as a positive number, the denominator will be a negative, and a positive divided by a negative will end up being a negative. And finally, to the left of that, whenever we choose any numbers to the left of -1, we end up with a negative number in the numerator, a negative number in the denominator, and so when we divide them, we end up getting a positive. Plus, 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 plus. So this breaks this down into three zones. There's a zone to the left of -1. The left of -1. And there's a zone to the right of +2. And in those zones, my function is going to be positive. And then there will be this middle zone between -1 and +2, where my function is going to be negative. Okay, now going back to the original statement, it did just wanted you to analyze this, figure out when this is true, x minus 2. When was this greater than 0? That was the original statement. So you need to figure out when is this going to be positive. And so as you can see, x plus 1 divided by x minus 2 is positive when x is strictly less than -1 or x is strictly greater than +2. In those two segments of my number line, this ratio will be positive. Okay? Or instead of saying it this way, we can also say that f of x is positive on -infinity up through -1 unioned with +2 up to +infinity, right? Either way is fine. Some questions might ask you the reverse. Maybe they'll ask you, when is this function going to be negative? And so we can say that the function will be negative between -1 and 2. Okay, so that should be enough to complete your homework. Let me know if you have any questions, problems, or issues.